To start off this video, I wanted to ask a question that is reminiscent of questions that we've answered before throughout this unit. What is the pH of a solution of hydrochloric acid in water with a concentration of HCl of 1 × 10 to the negative 8 moles per liter? Simple enough question, right? And as we often do in these pH sorts of questions, a good question to ask ourselves straight off the bat is, do we expect the pH to be greater than 7 or less than 7? Take a minute and pause the video and think about what you're thinking with this. Now, if we just proceed along the lines that we would usually take when dealing with a strong acid, we would start by recognizing that HCl dissociates completely, right? HCl is a strong acid, and so when we dissolve it in water, it's going to form hydronium or aqueous proton, H plus aqueous, and Cl minus to a complete degree, right? Only a forward arrow, meaning this entire 1 × 10 to the negative 8 moles per liter of HCl gets converted into H plus, and so we might go right to the molarity of H plus is equal to 1 × 10 to the negative 8 moles per liter. Great. And then we would do the usual dance with pH, noting that the pH is the negative log of that H plus concentration, and we would arrive at a pH of 8. Okay, simple enough. But this tends to fly in the face of everything we know about acids to date, right? Acids are supposed to lower the pH of aqueous solutions from 7, not raise it. How in the world did we add an acid to water and end up with a pH that we're very familiar with now as a basic pH? And the answer is there's a flaw in our process here. We haven't accounted for the fact that there's already 10 to the negative 7 moles per liter of hydronium in the water when the HCl is added. And so even though this sort of naive process leads us to expect that the pH would be greater than 7, that's not true. This pH is going to be less than 7. And on the remainder of this slide, we'll account for this, keeping in mind that at a concentration of HCl that's this low, I mean, the hydrochloric acid is not even the major contributor of hydronium to this aqueous solution. I mean, it could hardly be called a solution, really, right? This is a minuscule amount of hydrochloric acid in what is, for the most part, pure or nearly pure water, right? The major contributor to the H plus or hydronium concentration in this solution is the self-ionization of water, right? And actually, just to stay in line with what we've been doing in using H plus, this process is the major contributor to the H plus concentration, not the HCl, right? And so the overall concentration of hydronium in this solution is going to include this contribution from the HCl, but will also include a contribution from the self-ionization of water that's going to be pretty significant, right? Since this initially starts out 10 to the negative 7 mole per liter, which is already 10 times as big as the contribution made by the HCl. So the moral of the story here is that at very low concentrations of strong acids and bases, we have to be careful about just jumping right into a stoichiometry problem to calculate pH, because in fact at concentrations this low, even for a strong acid or base, ionization becomes reversible, and the self-ionization of water exerts a huge influence on the concentrations of hydronium and hydroxide at equilibrium. And this is just a rule of thumb, really, but at about concentrations of 1 × 10 to the negative 6 or lower, right, where we're lower than 10% of the hydronium concentration in pure water, where the self-ionization is at equilibrium and hydronium and hydroxide concentrations are equal. Below about 10% of that 10 to the negative 7 value, we're in the danger zone, where self-ionization of water is going to be a big player to the pH here. Now, if you think about how to determine the pH under these circumstances, one idea you may have is, well, okay, maybe if I'm given a Ka now for HCl, because now under these extremely dilute circumstances, I have enough H plus in the original water to actually push this equilibrium back toward products. If I'm given a Ka here, maybe I can just use an ice or a rice table to solve this, starting with an initial concentration of H plus that is 10 to the negative 7 molar, initial HCl that's in this case 10 to the negative 8 molar, and proceeding to solve this equation. This works sort of, but is complicated by the fact that while the equilibrium equation for HCl ionizing in water will hold true, Kw being equal to the product of H3O plus and OH minus molarities is also going to hold true. And so solving this system is going to require solving a system of equations, which is beyond the scope of Chem 1212K. This is more akin to something you might do in an analytical chemistry course. All that said, I think really the punchline of this video is that the pH here of this solution is going to be less than 7 still. It's going to be something like, 6.99 or something like that, right? Very, very close to neutral, but still less than 7 on principle, right? Because adding an acid to water cannot possibly lower the hydronium ion concentration from 10 to the negative 7. So this 10 to the negative 8 HCl that we're adding does make a positive contribution to the hydronium concentration. And of course, for bases, the same holds true. Even if we add very, very tiny amounts of, for example, sodium hydroxide to water, that will still cause a decrease in the hydronium concentration and a pH greater than 7 as a result. It might be something like, depending on the concentration of base that we add, it might be 7.01, right, or something like this. Still basic on principle, though, and conceptually we want to make sure we understand that even dilute acids and bases still have kind of the rational effects on pH that we would expect based on what we already know.